right, today we're going to take a look at section 7.2, operations on decimals. Specifically, operations, we're talking about your four-function calculator operations, right? So like addition, subtraction, multiplication, division kind of stuff. That's what we're going to be looking at today. So for starters, we're going to take a look at addition and subtraction. Addition and subtraction are harder for fractions than multiplication and division are for fractions. But with multiplication or with decimals, they're actually easier. So in order to do addition and subtraction, we're going to line up the decimal point, and then we're going to add and subtract. Everybody likes to tell me like normal. It's really not normal. It's just like you've normally done, which means like what you do with whole numbers. So if we have 4 and 33 hundredths, and then we have 3 and 26 hundredths, the decimal point lines up, and then we add as we do with whole numbers. So there's lots of just ways that you can do that without going too far away from where we are right now. Those of you who've had number theory, remember some of those. We're just going to stick with the standard algorithm. So if none of that made any sense to you, just don't worry about it. We're just going to do it the way you've typically done it in the past. We're going to start on the right-hand side. 3 plus 6 is 9. 3 plus 2 is 5. We bring our decimal point down, and then 4 plus 3 is 7, right? So just typical, but we've got to line up the decimal point. They don't always have the same number of decimals afterwards. For example, I could have been given this 4.33, and I could have been given 3.2658. I don't line it up with the last digits lining up. I still line it up with the decimal points lining up, so that is key here. A stock's price dropped from $63.28 per share to $27.45 per share. What is the loss on a single share of this stock? So what do I have to do with this question? Line it up and subtract. Correct. So the first number, the one that's the larger that we're starting with, was $63.28. The smaller was 27, lining up the decimal, 45. And we'll subtract. All right, so we'll start on the right-hand side. 8 minus 5 is 3. How about 2 minus 4? Can't do that the way it's written. We'll need to regroup, right? Or you might be familiar with the phrase called borrowing. So we're going to take this 3 and we're going to change it to a 2. And we're going to take one of those, which in essence right now is a dollar bill, and turn it into dimes. So previously I had 2 dimes. I take my dollar bill and turn it into dimes, and I get 10 dimes, right? Now I have my 10 dimes plus my 2 dimes, I have 12 dimes. That's literally what we've done. And you could do this with money with kids, right? If they're familiar enough with money for it to matter, right? You can also do it with base 10 blocks, and you can do it from that perspective where they can see them piecing together. We'll talk more about base 10 blocks later. All right, so 12 minus 4 would be 8. There we go. We bring our decimal down. Now again, I have to do some regrouping because I have 2 minus 7. So we'll regroup. We will take 1 away from the 6 to make it a 5. That's actually the tens place, so it's like taking a $10 bill and turning it into $1 bills, right? So now I have 10 $1 bills plus the 2 $1 bills I had before for a total of 12 $1 bills. $12 bills minus 7 would be 5. And then the 5 tens minus the 2 tens in the tens column would give me a 3. This is money in this context, so let's put a dollar sign on it, and then we're good to go. Okay, so far so good? Familiar stuff, very good. Multiplication. Multiplication, as with whole numbers, multiplication is that you multiply as with whole numbers, and then you count the number of places after the decimal point in all the factors, and this will be the number of places after the decimal point in your product. Okay, so I just need to show you what it is because it's kind of wordy description. It's accurate, it's just kind of wordy. So if we do the 0.3 and 0.7, it doesn't matter whether we line the decimal points up. They happen to be lined up here, but it's irrelevant. What this says I'm going to do is I'm just going to multiply as I would with whole numbers. So 7 times 3 is 21. Because everything else is zeros, there's no other non-zero numbers to multiply, I'm done with the multiplication. But what I do is I count the number of places after the decimal points in the numbers I just multiplied. There's 1, 2. There are 2 numbers occurring after the decimal point, right, in my 2 factors. So my answer needs to represent represent two numbers after the decimal point for my answer. And it would look like this. I want to talk to you about why it works, though, because that looks a little bit like mysterious, and it's really not, but it's not easy to see why it's working for us. It's much easier to think I'm just going to pull my decimal point down, just like it did with the addition and subtraction, because I already have a reason that I did that, right? So what's happening here? Well, we're going to think about it from the perspective of fractions. How would I write 3/10 as a fraction? 3/10. And how would I write 7/10 as a fraction? 7/10. And if I were to multiply, like we've done before, multiply across the top, multiply across the bottom, there's that 21 on top. And what's on bottom? Is it? It's 100. 100 on bottom, not 10 this time, right? There we go. Yeah, we're multiplying. 21 hundredths. Well, how do I write 21 hundredths? We just did that in section 1. It's a decimal point with a 2 and a 1. And you can see it coming about. So when I'm multiplying these values that are behind the decimal point over here, what I'm really doing is I'm multiplying fractions that have bases that are powers of 10. So I end up with a new denominator in those cases that's a higher power of 10 than I started with. Okay? But that's what's happening. I'm not asking you to do this every time, by the way. That's not my point. I just want you to know there's a reason that's happening there that's very much what we've already talked about. All right, let's look at division. So when we're doing division, we want to make the divisor, so the divisor is the number we're dividing by, a whole number by moving the decimal point in the divisor and the dividend an equal number of times, and then we divide as with whole numbers. So I'm going to write this kind of old school, where we put the 0.5 outside the division sign like this, and the 0.75 underneath it. Okay, this is how we would rewrite the expression we were given. What this is saying is the number on the outside of the house, right, over here, the 0.5, needs to be a whole number. And the way that I get it to be a whole number is by moving the decimal point, in this case to the right one. But I can't do it just there. I also have to do it to the number underneath the house. So I'll move it right one as well. So I'm not suggesting you need to rewrite this every time, but for the purpose of me showing you, I'll do it this time. This would be 7.5 underneath here now. Okay, so I have 5 on the outside, 7.5 underneath. Now I'm going to divide the same way that I would with whole numbers. So I would ask myself, how many times will 5 go into 7? Once. 1 times 5 is 5, and we subtract. Now, the decimal point will come straight up, right? Just like it would come straight down with the addition and subtraction. When I subtract 7 minus 5, I have a 2, and I bring down my 5 to make 25. So how many times will 5 go into 25? 5 times. 5 times 5 is 25, and I'm done because I have a remainder of 0. That's how I'll know to stop. It's going to get a remainder of 0. And the answer is the 1.5 on top. Okay? Again, why does this work? Well, instead of writing this as division, sort of, the way you learned it in like 3rd, 4th grade, I want to write it in division like in terms of fractions because it's easier to see. And I don't mean fractions the way I just did the last problem. I mean literally to write 0.5 as the numerator and 0.75 as the numerator and 0.5 as the denominator. Okay? So I'm writing the division itself as a fraction kind of division instead of as a long division problem. Okay, so if I want the denominator to be whole number, the way that I get that to happen and move that decimal point 1 over, which is my goal, is that I multiply by 10. But if I multiply by 10 on the denominator, I've got to do it to the numerator. That's a property of fractions. So that moves this to being a 5 in the denominator, and that same 7.5 in the numerator. And lo and behold, that's exactly what we did when we shifted them in the long division form. Okay, that's what's happening there. Is what we're really doing is we're multiplying the dividend and the divisor both by the value 10. And that's why that happens. All right, so those are our 4 basic operations. Any questions so far? Okay. So the other thing that's going to show up in this section is scientific notation. I do not teach scientific notation the way your book is probably going to explain it, or maybe how you've seen it before. So be prepared. It's going to look and feel a little bit different. Hopefully it's helpful. I mean, hopefully. Otherwise I wouldn't do it, right? That's my hope. All right, so first let's talk about what it is. Scientific notation is written as A, where A is a number between 1 and 10, a single-digit number, right? It can have decimals, but it can't be bigger than 10. 9 point something is the biggest. And the exponent on the 10 to the n is an integer. So that means it can be positive and it can be negative. It could even be 0, although that wouldn't be very helpful. Technically, it could be 0. So the n can be -5, but it can't be -5.4. Right? The n can be 22, but it can't be 22/7. Stuff like that. Okay? So when is scientific notation useful? Don't tell me never, because that's not true. When's it useful? What's it used for? Say again? Non-terminating decimals, not usually, actually. It's still not usually used for non-terminating decimals. It's a good guess. Emily?
I don't know if I've listened to this class, but like in science, they have us take those huge numbers and make them into the...
Okay, so you hit on the really important piece there. There's 2 of them. One of them is what you said. Really big numbers.
Yeah.
So can you think of something that's a really big number? I mean, like, practically you wouldn't want to write it out that far. Something would be like that. Like, can you tell me something that you would be using a really big number like that to do? Your checkbook's not it, right? You wish. The federal deficit might be, but that's not what I'm talking about either. Think back in terms of what Emily said about science. What are some things in science that show up as having really big numbers?
Distance to stars.
Oh, distance to things in our galaxy, right? Or outside of our galaxy. The distance to stars, or maybe other planets, right? Yeah, really big distances. That's one of the places you see it used in science. Yes? Really small numbers is the other one. And those are also used in science. Can you think of things in science that produce really small numbers that we measure with scientific notation sometimes? This is also not your bank account. You usually see it in chemistry or biology.
Like microscope?
Stuff with microscopes, the size of things that are really tiny, right? Organisms, or if you go down to atoms or something like that, where you're talking about how small something is, that we would need a microscope if we even could see something that small, right? Okay, so scientific notation's purpose is for really big and really small numbers, which is not most of the numbers we use in everyday lives as teachers, but you don't know who you're teaching. And you're going to be teaching some kids who are going to go into science, and it is going to be really practical and very necessary for them to be able to work with scientific notation. It's also actually really nice because we don't want to have to write out those numbers really long if they're either really small or really large. So we have 2 things that we have to be able to do. We have to be able to take one of our standard numerals and put it in scientific form, or we have to be able to take a scientific form numeral, a scientific notation numeral, and write it in standard form. So this first slide is moving our standard numerals into scientific. So what we do is we move the decimal point to create a value between 1 and 10, and we count the number of moves we've made. This is the part that I do a little bit differently. A large number gives us a positive exponent, and a small number gives us a negative exponent. I don't have to count, but I don't have to worry, did I move left or right? So the reason I like to emphasize this is because large exponents correspond to big numbers, and that's a relationship that we should have established in our mind. And moving left and right changes if I'm going from scientific to standard or standard to scientific, and I have to remember which one's which. But it's always true that large exponents correspond to big numbers. I didn't say it right. Positive exponents correspond to big numbers. and negative exponents correspond to small numbers. It doesn't matter which direction I go, it will always hold. So let's take this number. Oh, I should probably clarify what I mean by big. It's really easy. Big is bigger than 10, and small is smaller than 1. It's the two ends of the numbers I'm looking to create anyway, okay? So this number, 298,000, big or small? Big, which means my exponent is going to be positive. Okay, it's good to know. All right, so the number that I'm working with here, I need to place a decimal point somewhere in here to create a number between 1 and 10. Where should my decimal point go? Between the 2 and the 9. You can write the extra zeros at the end if you really want them there, but if they're trailing zeros after a decimal point, you don't have to write them. So 2.98 is perfectly fine. It's times 10. And what I want to know is, we already talked about the fact that I'm going to have a positive number, exponent here. I want to know how many moves I made to put the decimal point right there between the 2 and the 9. So where's the decimal point before I put it there? At the very end. So it's over here. And I want to count how many places I went to get to the 9, to before the 9. 1, 2, 3, 4, 5. So my exponent then is 5. And it's positive because the number is large. Okay, think you got it? Okay, we're going to go the other direction now. Now we're going to go from scientific back to standard. So again, positive exponents, numbers large. Negative exponents, numbers small. Okay, these are things to keep in mind. And we're going to move the decimal point from where it is to make it either a bigger or a smaller number to correspond to that. And we move it the number of places that the exponent says. So like over here, my exponent said 5. I'm going to move it 5 places. All right, let's do one. This number says 3.2 times 10 to the negative 5. Do I have a big number or a small number? Small. I'm going to jot that down as a reminder to us for the moment. In the end, my number needs to be something small, which means smaller than 1. Okay, so right now, the number, I'm just going to write it bigger so I have more space, is 3 with a decimal point of 2. How am I going to move the decimal to make it smaller? Is it going to go this way over here to the left? Or is it going to go this way to the right? Which way is going to make it a smaller number? The left. Okay, so if I moved it to the right, like this, it would make a number that's 32. That's bigger than 10. That's why I don't want to do that one. So I want to move the decimal to the left. This is one place, and I'm supposed to be moving it how many? 5. So I've moved it 1, but I can't move it anymore. So I need some leading zeros in order to keep moving it. So you can just put a bunch of them in there. And then we'll just not include them in the answer when we're done. So I've moved the decimal point 1 time. How many more times do I need to move it? 4. Here's 1, 2, 3, 4. I guessed pretty well when I was randomly writing my zeros. Okay, so that's where it's going to end right here. You can either have the 0 at the beginning or not. It doesn't matter. So you can either write this as a 0 point, and then I have 4 zeros, and then 3, 2. Or you can just write it like this. Either of those are fine. And it meets the criteria. It's a small number, right? Yeah, it's a small number. We've moved the decimal point 5 times. All right. The next one we're going to take a look at is actually multiplying in standard, in scientific notation. So this one says to write the result of the following in scientific notation. Now, one of the things that we learn about you learn about in grade school, we talk about it in the first part of this book in chapter 3, I think it is the first time, is that multiplication is commutative. So commutative means you can shift things around and you can multiply in whatever order you want. That's actually really nice because that means I can put the numbers that look similar together, right? The 6 and the 8. And I can put the numbers that have powers of 10 together like this. And I can multiply them in a different order. Now that's making use of both the commutative property and the associative property because I've regrouped and I've reassociated things together. Now, what's 6 times 8? 48, good. And 10 to the 12th and 10 to the 15th we did back in section 6.3. What do I do in order to make that a more condensed version of that? I add the exponents. So this would be times 10 to the 27. Now, we've done the hard part, but my answer's not finished. Why isn't this done? Yeah, the 48 is bigger than 10. Now, sometimes when you do this multiplication, it'll still be within the number 10, like it'll be like a 9.2 or something, and you're fine and you're done. But this one's just not. It ends with a 48 down here, and 48 is not a number between 1 and 10. So where would I really want the decimal point to be instead? Yeah, between the 4 and the 8. I can't just put it in there and think that that's going to work. I have to make an adjustment. The adjustment I have to make is going to be to the exponent on the 10. 48, was it a big number or a small number? Big. So in order to compensate for the fact that I just made it smaller, I need to make my exponent bigger, right? It's a give and take thing. So if I've made my number smaller, I'm going to make I'm not going to use a dot here. I'm going to use an X because I've already got a dot down there. So I've got my 10, and it'll be to the 28th instead of it being to the 27th. I made the number smaller, so I'm going to make my exponent correspondingly larger. All right, estimation. Okay, there's more than one kind of estimation. The one you're probably most familiar with is called rounding. With rounding, we need to know where we're rounding to. So this says rounding to the nearest blank, because you can fill in the blank with whatever place value you want. You can round to the nearest tenths, you can round to the nearest millionths, right? Like you can round to the nearest whatever it is. The way that we do that is we find the location that we're wanting to round to. So let's say it's hundreds, like the DS, like $100 bills. Hundreds. It means you go to the hundreds place. You look at one place to the right of it. That would be the tens place. If that number is a 5 through a 9, we round the hundreds place up. If it's not, we leave the 100 place alone and we zero everything else out. That's rounding. Now, front-end estimation, what it does is it actually just keeps the front end of things and zeroes it out. There's no rounding at all. You don't look at how close you were. You don't look at anything. You just zero things out. So sometimes it yields the same thing that rounding does. Sometimes it doesn't. Okay? Now, it tells you that you're using the first value or the first couple of values. What that means is that oftentimes that you just choose which one you're going to do. So you might as well choose something that's not too far in. Yeah, Faith.
I would also say when you're telling younger students 0 to 4 round down, I wouldn't say round down. I would say stay the same.
Yeah.
Because they will try to actually round it down a number.
And I'll talk a little bit about that and how you can use that terminology, because a lot of books you use will actually say that too, whether you say it in this teacher role or not. And so we can talk about what it means to round down from that perspective too. That's a very good point. I agree. Oh, look, my slide's already filled out for us. Let's delete those. Evidently, I didn't get those cleared out. Or the last ones. My goodness. Look at this. Failure, failure. All right, let's do this now. All right. We have this number, 203 and 651 thousandths, and we're going to round as specified. The first says to the nearest 100. What number is in the hundreds place? 2. So right now we have 203.651, and the hundreds place is the 2. Okay, so what this means is I look at the next value after the 2. Let me use a highlighter. If it's a 0 or up to 4, what we would say is we round down. What we mean is we round the entire number down. So this number is going to be, because I'm talking about the hundreds place, it's either going to be a 200 answer or a 300 answer. It's one of the two, because $203 is between $200 and $300. So when we talk about rounding down or rounding up, we're talking about changing the number into either 200 or 300, not into 100, which is what Faith is trying to guard against, right? Taking that number and actually making it smaller. That's not what we want to do. That is the 2. So the 0 tells us I'm going to round down, or sometimes we would say round off, right? Just to zero everything else after it out. So since it is a 0, it means I'm going to go down to 200. Okay, for the next one, it says hundredths. What number is in the hundredths place? The 5. And we're going to be looking at the 1. So again, what that means my two options is to either go to 203.65, that's rounding down or rounding off, or I'm going up to 203.66 because the 5 would go up to a 6. Okay, the 1 tells me that I'm going to give me which of those two answers? The first one, the 6-5 one. Right, so this one right here is going to be my answer because the 1 rounds down or rounds off. Unit, what does it mean to say to the nearest unit? The ones spot. Yeah, so we use the word ones place and units place interchangeably. Something to be aware of because that is sort of the one that we do a little bit weird. What number is in my units place? The 3. Which means I'm looking at the 6. So this is like, especially if we can ignore the 1 on the minute, 1 on the end for a minute, you have $203.65, right? If you think about it from a dollar amount perspective. So if we round to the nearest dollar up and down, I have 203 or 204. The 3 either stays the 3, right? It stays, or it goes up. The 6 tells me what I need to do. I finally got one that's in the 5 to 9 range. And 5 to 9 range means I'm going to do what? Up. So this one's answer is 204. Okay, let's do one with some front-end estimation as well. Okay, so these questions, first of all, let me just tell you, they're not my favorite questions in their book. I don't think they're worded very well. They just say use rounding, and then they use front-end estimation, but the rounding is left very vague. It doesn't tell you what you're rounding to, and I don't think you see that very often in actual curriculum in classrooms, which is why I don't like these questions very much. But if I remember right from when we selected the problems originally, they're the only ones that ask the question about the front-end estimation in them. So if I'm going to ask you questions about front-end estimation, I got to use this question. Does that make sense? Okay. So in the case of a question like this, it means you have to pick what the place is that you're rounding to or estimating to. Now, it would not be helpful to make it too very long because the whole point for estimation is that it makes it quicker and easier to do. That's the whole point. So if I'm not going to make it quicker and easier to do, I might as well just do the actual problem I was given. You with me? So on this one, I would suggest we either do this to the tens place or to the ones place. Those are the only things that really make sense for this problem. So I don't want to do it twice. I just want to let you guys pick. Do we want to do tens place or ones place? Ones? Okay, tens. Oh, I feel like we've heard both now. Tens. Let's do tens. It'll be faster. Sound good? Are you good with that? Okay, we'll do tens place this time. So we're going to do this to the tens place. So A says rounding. So that's what we were doing before. So what this actually means is that I need to round the beginning values, and then I need to get an answer. So my children in my house sometimes confuse that, and they want to do it the other way. They just want to find the answer, and then they want to round it. Sometimes that actually gives you the right answer, and sometimes it doesn't, but it kind of defeats the point. The point was to make the subtraction easier. Yeah? So if we're doing this to the tens place, we're going to take the numbers that we were given and work with them. So this one's the 8. Is this 9 going to round this up to 90, or is it going to keep it down at 80? It's going to round it up to 90. Over here then, I have the 3, and I look at my 2. The 2, is it going to round this 30-something up to 40, or is it going to leave it at 30? It's going to leave it at 30. And then 90 minus 30 is 60. Okay, so this is the rounding version. Here's what front-end estimation does. Front-end estimation says, I don't really care what any of the numbers are after the number I care about. I use the same place value. We're doing tens place. The whole point is to compare these. So when I see 89.47, I don't care that the 947 is there at all. That 89.47 is just 80. You just keep the first number and you zero everything else out. Or you can think of it as always rounding down or rounding off or staying the same, right? That first value stays the same the whole time. The next one, 3216, would be 30. And of course, the subtraction gives me 50. That's what front-end estimation looks like. And you can see how, depending on the values we're given, they might actually look exactly the same, right? That's a possibility. And then it says, then perform the computation to see how close your estimates are. So we're actually going to take the numbers we were given, 89.47 minus 32.16, and subtract. All right, 7 minus 6, 4 minus 1, 9 minus 2, 8 minus 3, 5. And which of our estimations is better? Yeah, the 60, the one with rounding. And typically speaking, the rounding is a better estimate than the front-end estimation. It's rare when it's not, or when sometimes they match. So all of these should have dollar signs on them. I think they were dollars. They were not dollars. I totally lied. Never mind. I was thinking dollars because it had 2 decimal points, but it definitely didn't say that. Okay. This is the last thing we're going to do today, which means that we're not going to have time for group work, unfortunately. It'll just be part of your homework. You are going to need a calculator to do this problem. So grab one out if you have one. If not, just follow along, write along with us, look at it later. It's fine. Okay, a student tries to find, or tries to calculate 0.999 to the 10,000 on a calculator, finds that the answer is 4.5173346 times 10 to the negative 5th. Is this a big number or a small number?
Oh.
Small. How do you know? Exponent's negative. This is a small number. So if I were to actually figure this out in scientific notation to standard form, I'd move that decimal point 5 places that way to make it smaller. It's a very, very small number, right? It's very small. That means it's really close to 0. So the student wonders how it is that you have a number that's 0.999. It's really close to the number 1. And it's raised to a power, but then it results in a number that's almost 0. Sort of seems counterintuitive, right? I took the number that's practically 1, raised it to a power, and all of a sudden I got back down to 0. How do you respond? So we're going to explore a little bit with our calculator with this. I need to write this down, so I'm going to use this like this. So what we're going to do is we're going to take that 0.999 and explore a little bit with it by raising it to some powers that increase. So I'd like for you to do 0.999 in your calculator squared. If you do that, you're going to get 0.998001. So it's probably worth noting, did it get smaller or bigger? It's a smaller number. There's more digits, but it's a smaller number, right? And then what I want to do is I want to do that power of 2 again. So in your calculator, I don't know if yours is like mine or not, but it can take the previous line that's already there, and you can just hit square, and it will take that previous answer, and it will square what you just did. So in essence, what I'm going to do right now, I'm just going to write it down in words, is that I'm going to square it again. So what I'm actually squaring is the 0.998001, and I'm going to write it with 6 decimals. This will give me 996006. I actually have that same 0.999, and if I raise it to the 2 twice. 2 times 2 is 4. This is 0.999 to the 4th. Once again, did it get smaller or bigger? Smaller, but negligibly, right? Like not very much smaller. I mean, it's still 99 cents, almost $1 if I'm, looking at it from the perspective of money. It didn't change that much. And we're going to do it again. So if I square it again, I get 0.992028. That is 0.999. And I take the 4, multiply it by 2, because I raised it to the power 2 again. That's 8. I now have an exponent of 8 on my number. We're going to do it a few more times. So this is sort of a dot, dot, dot. We're going to keep squaring in our calculator. So we're going to square, and then we're going to square again. And all of a sudden now we no longer have 99 cents. We have 0.984119. These are not multiplied by these. They're just another expression for them, by the way, right? And my powers are doubling every time. And then I get 0.96, 8491. That's 0.999 to the 32. I have 0.937975, 0.99964. I want to do 4 more lines. Okay, you can fill them in later if I'm going too fast. I'm sorry. I recognize that I'm running out of time and I'm trying to get you out of here. This next one is actually the first time I go under the 0.9 mark. So this is 879797. 0.999 to the 128. So we're finally to a power that's bigger than 100. And we're finally at a value that's smaller than 90. One more time and I jump down big. This is a big jump, right? We were trickling down a little bit before, just trickling down like nothing at all. But now we jumped really pretty big. But when we're doubling our exponent, that's why. So this is a 256 exponent compared to the 128 before. The next one's 599142. Again, doubling my exponent gets me to 512. And I'll do one more and we'll stop. The last one that we're going to see actually jumps down again massively. 971. This is 0.999 to the 1024. Okay, so here's the deal. Every time we multiply by a value smaller than 1, like between 0 and 1, a positive value, smaller than 1, the result is smaller. It gets smaller every time. But take a look at how many times we're supposed to be doing that according to this particular direction. 10,000 times I'm multiplying by something and making it smaller. It's a lot of times. I only went to it slightly bigger than 1,000. All right, slightly bigger than 1,000, and I'm about 1/3 of where I was. So if we do this 10,000 times, that's what's creating this sort of a decreasing hole, right? Where it continues down this hole, is because it's getting smaller every single time, 10,000 times. But it's really important for you to realize as future educators, from some of you wanted to work with the little ones, that you do not tell your students multiplication makes things bigger. That's a misnomer. It didn't work here. Every single time I multiplied and it got smaller, right? But how many of you have heard your teachers say that before? I have. I've probably been guilty of doing it myself. Because when you're working with whole numbers, it does, right? But once you start working with decimals and fractions, that's not going to hold.